This is section or part 6 of the module 4 lecture. In this part, we're going to talk about the multiplication rule. The multiplication rule is to find the joint probabilities. And we have two versions of this multiplication rule. One when the events are not independent, and one where the events are independent. In this case, we're looking at two events, A and B. And in the first part, we're looking when these two events are not independent. So the joint probability of events A and B can be calculated as the probability of event A given event B times the probability of event B, which is the one we're conditioning on. Or you can calculate the joint probability by multiplying the probability of event B conditioning on event A times the probability of A. And here we're conditioning on A, that's why we'll multiply by the probability of A. So notice how the probability of the event that we multiply by the conditional probability is that of the probability of the event that we're conditioning on. All right, now in the second version, if two events are independent, then the conditional probabilities simplify to use the probability of the event that we're not conditioning on. So the probability of A given event B is just the probability of event A, and the probability of B given event A is just the probability of event B. For that reason, then the multiplication rule when the events are independent simplifies just to the product of the probabilities of the two events. So the joint probability when the events are independent is just the multiplication of the individual probabilities. This is a very important situation that we will be using a lot as we move forward in the course. All right, let's look at some examples to see how we can use the multiplication rule to calculate joint probabilities. In the first example, we're looking at U.S. medical school seniors that applied to a residency program in 2007. So 93% of those students were matched to a residency position, and 74% of those seniors that were matched to a residency position were matched to one of their top two choices. So there are two questions in this problem. Number one, what is the probability that a randomly selected senior was matched to residency position and it was one of her or his top two choices? The second question is, what is the probability that a randomly selected senior matched to residency position did not get matched with one of the senior's top two choices? So when you solve these problems, the very first thing to do is identify the events that they are talking about. And here I underline the text that corresponds to the events that they are talking about in each of the questions. So in the first question, they're asking us to find the joint probability that the student was matched to a residency and was his or her top two choices. In the second question, they're asking us the probability that the senior was matched to a residency position but did not get matched to the top choices. So once you highlight the events that are of interest, then you can interpret these numbers in the problem a little easily. So this 93% corresponds to the probability of the event matched to residency, and this 74% corresponds to the probability of seniors that were matched to residency position were matched to one to their top two choices. Another way of expressing this is saying that it's 74% that a senior was matched to his or her top two choices given that it was matched to residency position. So with this interpretation, now we can start solving the problem. So my suggestion is always write down the events that you identified. So in this case, event A is matched to residency position and event B is matched to one of the top two choices. So as we saw from the information given in the problem, the probability of being matched to residency position is 0.93, and the probability of match to one of the top two choices given that it was matched to residency position is 0.74. So to answer the first question, they're asking us for the joint probability of match to residency position and match to one of the top two choices. So that joint probability is just the product of the conditional probability times the probability of the event that we're conditioning on. In this case, is the probability of match to one of the top two choices given that it was matched to residency position times the probability of being matched to residency position. That's 0.74 times 0.93. That gives us 0.66688. All right. So now once you obtain the result, you need to interpret that result. And here we see that the probability that a randomly selected senior was matched to residency position and it was matched to her or his top choices is 0.688 or 68.8%. All right. So this is part A of the problem. To solve part B, then we need to state the other event that I mentioned, which is not matched to one of the top two choices. And if you see, this is the complement of being matched to a top two choice. And then you see that event A matched to residency position. You either were matched to one of your top two choices or you were not matched to one of your top two choices. So because these two make up the event A, then we can write this, the probability of being matched to one of the top two choices given that you were assigned to a residency position plus the probability of not being matched to one of the two top choices given that you were matched to a residency position must be 1 because they complement each other within this one event. So now we're going to use this total probability expression to find the probability that we're looking for. That is the probability of not being matched to one of the top two choices, given that the student was matched to a residency position. So again, just replacing the numbers in this expression, we obtain 0.26. So interpreting this number means that a probability that a randomly selected senior matched the residency position did not get matched to one of the top two choices is 0.26 or 26%. So in this example, we use the multiplication rule when the events are not independent. And we took advantage of both the conditional probability and the complement rule to answer the second part of the problem. So we're ready to use these concepts to solve problems that perhaps may not be as straightforward as the first part of this problem. All right, let's look at another example. In this case, we're looking at the reliability, that is the probability of not failing of a power supply. This is the part that provides power to computers. And the reliability of these power supplies is 99.7% or 0.997. Now, two power supplies are installed so that they operate independently and they are used to maintain a computed network. So the question here is, what is the probability of a network failure caused by a power supply failure? All right, so in this case, we use the complement rule to find the probability that a power supply fails. So the power supply fails is the probability of a power supply failing is just 1 minus the probability of the power supply not failing. So that's 1 minus 0.997, which is 0.003. All right, so now we're going to use the multiplication rule to determine the probability of failure of the network. So the probability that the network fails because the power supply fails implies that is the joint probability of the power supply 1 failing and the power supply 2 failing. Now these power supplies are installed so that they're independent of each other. So to calculate the probability that the network fails because a power supply failed, what we do is we just simply multiply the probability of failure of each power supply, which in this case are the same. And if you multiply 0.003 times 0.003, you get 0.00009. That is, this network will rarely fail because of a power supply, because the probability of failure is 9 in 1 million or 0.0009%. So in this example, we use the fact that these two events are independent, and we just simply multiply the individual probabilities. All right, here's another example, and the reason I included this example because it's very troublesome how people misinterpret probabilities. In this example, and this is a real case, and I put the reference paper if you're interested in reading it. And here, another elderly woman is robbed by a younger white woman with a blonde ponytail. A witness, upon hearing the older woman screaming for help, sees a woman matching the description get into a yellow car driven by a black man with a beard and a mustache. So a white woman with a blonde ponytail married to a black man without a beard are arrested, charged, and convicted based on the testimony of an expert. All right, so this expert gave testimony about the product rule of probabilities, and he says, well, then the prosecutor said, well, I'm going to assign some subjective probabilities to that different situation. So what would be the probability of finding a yellow car? Let's say 10%. The probability of men with a mustache, let's say 0.25. The probability of a woman with a ponytail, say 0.1. The probability of a woman with blonde hair, 0.333. A black man with a beard, the probability of that is 0.1. And the probability of an interracial couple in a car is 0.001. And so he made up this probability, the prosecutor. And then using the expert's testimony on the product of probabilities, he just multiplied all these probabilities. And he found, and he used this in his argument, it says, well, multiplying these probabilities, there was but one chance in 12 million that any couple possessed the distinctive characteristics of the defendants. And because these probabilities are conservative, the actual chance that anyone besides these defendants being there, having every similarity, is actually somewhat like 1 in a billion. So based on that argument, the jury convicted the couple. Well, unfortunately, no one in this jury knew about the multiplication rule. It didn't know about the independence of events. And of course, they make a big mistake, because the fact that this couple is a very rare occurrence, that doesn't mean that they were there and that they were the ones that committed the crime. So a big confusion here. So you need to think carefully and remember that the only time that you can multiply probabilities is when they are independent. And again, assigning subjective probabilities is very dangerous to do that without evidence. Not only that, this prosecutor went all the way to saying, because this is such a rare event, they must be culpable. And that doesn't make any sense. All right, if you read this paper, you will see that the defense didn't like the argument. They looked for other experts and they rebuked this argument. And eventually, this couple was declared innocent. But I like to include this example in my lectures because I want to emphasize how important it is to understand these concepts of probability and when you can multiply probabilities and when it is appropriate to assign subjective probabilities. So keep that in mind, and I invite you to read this paper right here. You find that it's free. Use the online search and you will find it. All right. In the next segment, we're going to talk about the addition rule. So I will stop here.